Hello, 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 I'm back. Okay, so where were we? So we just finished the um alternating series test questions, and now we're gonna go to absolute convergence. So this says if the sum of the absolute version or the absolute value of a series converges, then so does the sum of just that series. Warning, if the absolute value of this diverges, then no conclusion can be made about the sum of the non-absolute value version of the series. The series may still converge or diverge. Let's do this example. Determine whether each series converges by checking for absolute convergence. So we see here that if I were to extend this to be the absolute value, I'm going to go ahead and write it out first. We see that this term no longer holds any value, because this just alternates between -1 and +1, and we know that under the absolute value, or coming out of the absolute value, a -1 and +1 are just both 1. So really, this is the same thing as writing it as 1 over n to the power of 3. And then from here, you would just check that limit, the limit as n goes to infinity of 1 over n to the 3. Is that happening on the screen? It's like a weird glitch happening. I'm gonna go ahead and unplug the camera and plug it back in real quick just to see if that fixes it. And then I put it back in. Whoa, that's a new glitch. Hold on. Back. It's frozen, but it's on. Let me go ahead and just turn the camera on and off again here. Okay. So yes, okay, so we'll see if that glitch does keep happening. Limit here, we know that that's going to be 0 because that'd be bottom heavy. Over here, we have a similar effect. Again, writing the absolute value. Oh, wait, so that means that if the absolute value converges, then this one also converges. So via absolute convergence, our original sum converges. Okay, and then this one, you take the absolute value of this, and you have a similar result where that top part is not going to matter because it's just the same thing as just writing 1 over n, because under the absolute value, you take the limit as n goes to infinity of 1 over n, and that's going to equal 0, and you have the same answer here via absolute convergence. Our original sum converges. Okay, let's go ahead and now jump here. Suppose a series, or the sum of the series, is a series in which is a series which may have both positive and negative terms. If the absolute value of an converges, then an must also converge. And in this case, we say that an converges absolutely. If the absolute value of an diverges, but we later see that an converges anyway using some other test, we say that that sum converges conditionally. Elsewise, if none of these two work, then you just say they diverge. So every series fits exactly into one of three categories. Converges absolutely, converges conditionally, diverges. Example 2. Determine whether each series converges absolutely, converges conditionally, or diverges. Okay, well, from here, we're going to go ahead and take the absolute value of this, which I'm going to skip this part for this, because we know just gets rid of that top term, so we can really rewrite it as 1 over square root of n. And something I have been skipping is because we know n is positive, there's really no need to keep the absolute value. So you don't have to redo the absolute value here as well. In fact, I should technically just, from here, simplify it like that. Okay. Same thing here. I should also just simplify like that. And we can already see that this will converge. This will converge because of it being a bigger power on the denominator, which is bottom heavy, so that means it'll go to 0. So from here, we say if the absolute value converges, then an must also converge. In this case, we have converges absolutely. Um, let's keep it going. We have two more. Let me just double check that I didn't miss anything. Oh, wait a minute. Let me see something. I think I did mess up. I know what I messed up. I messed up on, let me see, this technicality. Um, I accidentally would use if the series converges, but it's supposed to be if the sum converges. So, if this if the series they all do as n goes to 0, as n goes to infinity, they all do go to 0. That's just true no matter what. However, the sum is the tricky part. So, like for example, all of these, if you did a divergence test, you would have gotten 0, which means it's inconclusive. But for the sum being convergent or divergent, you would acknowledge it being for these, actually for all of these, you would use the logic of a p series. So you would say p series. P is greater than 1. In this case, p is 3. Same thing over here. Um, p series. P is, so P is greater than, let me just double check that. Hold on, because I want to make sure that I'm saying this correctly. Where's our P series? Integral test. Here. Um, okay, well, here we actually have it to where it says P is, um, it's not supposed to be equal to 1. Okay, so for this one, we can't say P series. But we need to show that the sum does converge. And for here, we know that the number will get smaller and smaller. So you can say that the sum does converge, but by what method? It's not p-series. I mean, it kind of is p-series over here a little bit. Maybe we can do the integral test. Let's go ahead and do the integral test because we know it's a function. If we were to plot 1 over n, it is decreasing over time. So let's actually do the integral of that. So I'm going to erase this because this is not relevant. And this because this is not relevant. This as well. Okay. So for the integral test, we just do the integral from 1 to infinity, but 1 over, let's do, would I do x or n? I mean, you could do either or. I just forget what I've been doing in class. I think, yeah, so I relabeled it as x. So I'm going to go and relabel it as x2 dx, okay? So from here, we go ahead and just making sure, because this says if they are both converged or they both diverge, so the limit has to equal something. So in this case, you have ln of x, no, yeah, of x being from, oh, I forgot to write here, I'm just gonna go ahead and make the adjustment. I forgot to write that it is going to t, where the limit as t goes to infinity. So it's going to be from t to 1. So that's ln of t minus ln of 1. And then, oh, I keep forgetting to write the limits. Limit, I'm just going to write here, limit as t goes to infinity of ln of t minus ln of 1. So that's going to go to infinity, and that's going to go, well, that's just actually 0. ln of 1 is 0, right? Let me double check. ln of 1 is 0. So it's just going to be infinity. So this means that this diverges. Um, so it's actually going to say that because the absolute value of this diverges, then there is no conclusion we can make about the absolute convergence at this moment. So via absolute convergence, let me go ahead and just rewrite it as no conclusion because absolute value diverges. Okay. You just make sure. Yeah. Oh, you know what we could have used? Could we have used harmonic series? I wonder if some of you even are yelling over the TV, or yelling over the computer. Like, yeah, you could use harmonic series, dude. Let me see. Where is harmonic series? My, yeah, harmonic series. Wait. No, we talked about harmonic series more than once. Am I tripping? Um, Stopping harmonic series. Okay. Oh, look, the exact same thing we did. Oh my gosh. So sorry. All right. Now, okay. So let's go ahead and do the second example. Sorry about that. Okay. Determine whether each series converges absolutely. converges conditionally or diverges. So we see here it being written as the square root of n. We can tentatively take a b, and because, again, you're not doing this, you're doing it this, you can rewrite it as 1 over n to the power of 1 half. So if n to the power of 1 half, that means that it's a p-series problem and it diverges because p, which is 1 half, is less than 1. Okay. So I was falling for the trick that I've been telling you all not to fall for, that I keep falling for. If I keep wanting to check that the series is convergent, but not the sum of the series. Okay. All right. Let's see. So we saw that the absolute version is convergent. I mean, is divergent. But now we need to double check that the non-absolute version is somehow convergent anyway. Because now we've just narrowed it down to either converges conditionally or diverges. So in this case, what can we do? Well, what we can do is, and we kind of already did it by like accident, using the previous testing, the alternating series test, we first check if the limit of this, of the limit of the non-alternating part goes to 0, which, like I said, we accidentally checked. Which it does. And then we need to check if it's steadily decreasing, which we can definitely check either way. I'm gonna check with the way of writing it like this. Square root of n plus 1 is less than 1 over square root of n. Yeah, square root of n is less than square root of n plus 1. Doing cross multiply here, and then you can just square both sides. N is less than n plus 1, which is just true. So it does decrease. So thus, via the, what is it, the absolute convergence and the alternating series test, the sum is, or not the sum is, the sum converges conditionally. So we used first the absolute convergence, and we saw that we were not able, under the absolute version of this problem, get it to be convergent because we just use the logic of a p-series. And the p-series says that whenever your p is less than 1, it diverges. Whenever p is greater than 1, it converges. So therefore, the sum converges conditionally. Okay. Part 2. Okay. So let's go step by step. First, let's rewrite this to be the absolute value version, which is just going to be, well, I don't have to write the absolute value. I'm kind of just skipping that part. It's just 1 over n squared plus 6. So we need to ask ourselves, okay, well, does this converge? And for this one, we could do the integral test. We could do the, let me see. Could do the integral test. We could do the limit comparison test. Mm, let's go ahead and just so we can practice, I think we can do the limit comparison test. So I'm gonna pick um just an easier version of that series, which is just n squared. So let's go ahead and pick it to be n squared. So if an is 1 over n squared plus 6, bn is 1 over n squared, which really just becomes an over bn. We're doing the limit as n goes to infinity. It is um let's see, it's going to be n squared over n squared plus 6. If we factor out n squared from the top and the bottom and cancel them out, we have 1 over 1 plus 6 over n squared. And if we apply limit, we get 1, which does not equal 0, which via the limit comparison test. Sorry, too far. Via the limit comparison test, L has to be a non-zero term, then they either both converge or diverge. And we know that this guy, this sum over here, converges because of the logic of P series. P series, P is equal to 2, which is greater than 1. Okay, let's see. For fun, because it does decrease, yeah, I'm pretty sure this does decrease over time, especially after 1. I'm gonna go ahead and do the integral test as well, just to convey to you guys you can do whichever one you want. So the integral test from 1 to t, where the limit of t goes to infinity, is 1 over n squared plus 6, which you can technically, let me see, can we do this integral right away? It feels like you could have. Hmm. Can't factor this either because it's how many zeros. Maybe you couldn't have even done this because you can't make a U substitution that's not there. Can we do a trick of the trig substitution? Yes, I want to see you can because you can do here. Hold on, let me just. I don't have our notes handy, but I can definitely just pull up the. I know how to Google it. Trig sub tricks. What is it? Oh wait, it's for when they're. That's right. The square. Wait. Yeah. Oh no, I'm wrong. I'm definitely wrong. Um. Then why was I thinking of trig substitution? That's so funny. I overthought it. Trig integration. It's just a trig integral, isn't it? Yeah. I just legit overthought it. Okay. Because we know that um arctan derivative integral with we know that um for here I just literally googled it for arctan that whole thing becomes the box arc tangent of, what is it? X over this square root, so square root of 6. Yeah. And then I'll go ahead and let the 1 over square root of 6 escape in the front, t1. And then we have the limit as t goes to infinity. So for here, the limit as t goes to infinity, I'm going to let the 1 over square root of 6 escape. And we have arc tangent of t over square root of 6, and then minus arc tangent of 1. Oh, 1 over square root of 6. So for that one, you don't get a specific answer on our unit circle, but we know this is not anything, like this is just going to be, um, this is just going to be like a value. It's not like, it exists, it's not fake. That's not the way I mean it, but it just sounds like it. That's what I said. But if I do literally arctangent of 1 over square root of 6, you get this number. So this it exists, but you can leave it as that to be specific. However, for arctangent, as t goes to infinity, regardless if it's divided by square root of 6, we know that this will go towards infinity. And this guy's upper limit is pi over 2. I'm just double checking that, because I seem to be forgetting a lot of my basic math today. Yeah, it's pi over 2. So we have 1 over square root of 6 times pi over 2, and then minus, I'm just going to rewrite that, which, despite all of this, we should acknowledge that this is just going to equal some real number that does not uh equal 0. So, oh wait, excuse me, I'm forgetting my test. This is an integral test. So we know that this is just a bona fide number. So this just tells us that if the integral converges, then the original sum converges, which via the um what we're doing. Sorry. We keep jumping from test to test. Via the via the absolute convergence, we've seen that the whole thing converges absolutely. So here I'm gonna write like this. Via the absolute convergence combined with, either in blue we did the limit comparison, and then in pink and purple, we did the integral test. We can say our sum is, or we could say our sum converges absolutely. I keep wanting to say is. Converges absolute. Okay. All right. Next, this sum. Okay. So from here, we're going to do the absolute value version. This would really just gets rid of this. So we're doing the sum, n goes to infinity of n squared over n squared plus 4. From here, we could just think of what we can do here. We could do limit comparison again, but my issue here is that I guess it's not wrong, but if we're gonna at one point reach the what is it? The um if we're gonna do this sum, oh, I guess we don't have to check if the alternating series, right? Because we won't know. Trying to think of how you could come about this organically. Hmm. Well, you know that the limits. I guess you would just start with the divergence test. So we can start with the divergence test there. Oh, well, I guess we couldn't because that would equal 0. So I guess we should, let me see. Just double checking that I'm remembering my stuff. Divergence test is a series in which if this doesn't equal 0, then the series diverges, which here, I can already see that the limit, then goes to infinity of this will be a balanced equation, which will be equal to 1, which does not equal 0. So therefore, via divergence test, or never mind, I'm not going to write the answer yet, but this is just divergence test at the moment. So we see that via the divergence test that this guy does not converge, it diverges. But recall the prompt for the absolute convergence, which stated that even if this diverges, we should check if just the series converges anyway. And because it's an alternating series, we're going to use the alternating series test. So let's go ahead and use the alternating series test, which states that first the limit of the non-alternating part, which is just n squared over n squared plus 4, goes to 0, which we already saw that it does not go to 0. And is it steadily decreasing? Technically is, but either way, we know that it equals 1, which does not equal 0, which fails the AST. Let me just double check our prompt. So we found that this diverges. Oh, sorry, wrong thing. So the alternating series test. If we found that it does not equal 0, this test does not apply. In this case, the series diverges from the divergence test. Because if the limit here, because if we figured out that this doesn't converge to 0, then this limit of the alternating part times this doesn't equal to 0. Which means that for this specific sum is divergent via the divergence test and checking the alternating series test. So that's the caveat there. We first checked if the absolute value would work. Oh, well, I guess checking the alternating series test slash the absolute convergence. Because we see here that in checking the absolute version, we do not get a zero limit. We get a 1, which tells me that this fails the divergence test. Well, this sum fails the divergence test. So if the absolute value does not converge, it diverges, then we have to check this guy. And this guy involves a different test, which, funny enough, is very similar. So, as long as we have this match shown in some diction, like for example, this was a test question, we need to see some of this like verbiage being happened. So just please keep that in mind. There's some liberty I'm thinking about because it's an online test. I'm thinking about maybe like giving you guys like you will use blank 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 for this test, or you could use blank 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 because like for example here you don't have to use the integral test, you could have used limit comparison, but I'm thinking about doing that just to make it more streamlined, but I don't know. um I need to actually probably this video is coming out Wednesday, so Thursday's video you'll have a definite answer. Okay. um and that's gonna go ahead and finish that part. Let's do the ratio test. Okay, so a couple of clarifications for just power notation that I feel like I need to do. No shade, it's just a general thing. Um, a to the power, x to the power of a plus b means x to the power of a times x to the power of b. N factorial, you split that up to be n times n minus 1 times n minus 2, and you keep going until you reach 1. Same thing for over here. This can be written as n plus 1 times n factorial. And we know for here, you have to go in steps. So steps of 1. So in this instance, if I want to get to, like, let's just say 2n, I would do 2n plus 2, 2n plus 1, and then 2n. And notice how you're just trickling down. You're going step by step by step. Okay? So it's a counting problem here. This series here converges because it's geometric series with the ratio 1 over 2, where the absolute value of r is 1 over 2, which is less than 1/2. Recall r. In the context, r is the ratio of every two successive terms. Here, it's pretty straightforward to get what r is in terms of this ratio idea. Now, r can be elaborated because r is just given as a numeric value. But what if it wasn't always a numeric value? This series, n over 2n, is not a geometric series because the ratio is not a constant. So now the ratio formed is actually an expression with the variable itself. But as n increases, this value approaches 1/2. Thus, by the terms of series, as n increases, it's almost like a geometric series. So we can expect this series to, in a similar way, also converge. This is the idea behind the ratio test. The ratio test. Suppose you have this series, and it is a series with non-zero terms, and the absolute value of one entry over the other entry, a side-by-side ratio of two terms, is equal to L. If this L is less than 1, then this sum converges absolutely. If this L is greater than 1 or is infinity, then this sum diverges. And lastly, if this L is equal to 1, the test is inconclusive. The ratio test can be used with series with negative terms. It checks for absolute convergence as well. So keep in mind, the idea of an absolute value shouldn't stump you. Or the idea of it alternating because of the absolute value shouldn't stump you, is what I want to say. Okay, so we have, I think, 3 problems. Yeah. All right, let's go. So it says examine each of the series for convergence using the ratio test. So we have this set up here. I'm going to go ahead and just set it up. Limit as n goes to infinity of the absolute value of the n plus 1 version of this. So n plus 1 squared over 2n, and then n squared, 2n plus 1 over 2n. By this point, none of the values are going to be negative. Everything's squared, so you don't even have to write the negative value, the absolute value. And I'm going to go ahead and rewrite this so it's not such an ugly fraction. So we have the limit as n goes to infinity of the following expression, n plus 1 squared to n plus 1 times 2n over n squared. Okay, so for here, this would cancel out to where you just have a 2 left over, or 2 left over on the bottom, so 1/2 would escape. Doing the limit as n goes to infinity of n plus 1 squared over n squared. For here, you're better off just expanding that top part. Oh, or you can use Hopital's rule. Yeah, because this will go to infinity, that goes to infinity. Uh, would that be messy? I kind of won't. Let's try it. Why not? So it's 2 and then n plus 1 to n. No, yeah, you should still do. Actually, no, because then you're going to do what I wanted to do. You could. First, I'm going to expand that a little bit. 2n plus 2 over 2n. You would factor out the two n's, and you're left with, let's see, we'll factor out 2 first. So you have n plus 1 over n. And then you could just treat this as a balanced equation. Or I actually could have done that here and you just treat it as a balanced equation. Um, but in this case, actually no, because you have 1/2. Oh, you factor out 2 from the top and the bottom. JK, JK. I don't know why I just forgot. So you can use that as a balanced equation. Either way, you should just get the answer as 1/2. For here, you could have expanded it out and see that as well. That's what I wanted to do. Got n squared plus 2n plus 1 over n squared. That's balanced. So you would have also seen that the limit of this is 1 times 1/2, which is just 1/2. So now we have the actual limits. So the limit is 1/2. And via the ratio test, we have things to check. If it's less than 1, then it converges absolutely. If it's greater than 1 or infinity, diverges. If it's equal to 1, it's inconclusive. It's less than 1. So we have that it converges absolutely via the ratio test. Okay. All right. Next one, we have this alternating sum looking thing, but we can go ahead and just do the ratio test. So the limit as n goes to infinity and for this, I'm going to clean it up a little bit already. Because it says the absolute value of an plus 1 over an. I'm just going to rewrite that as the an plus 1 term multiplied by 1 over the an term. So I'm going to do that here. We have an plus 1, which is -1, n plus 1, and then we have n plus 1 factorial over 10 to the 2n plus 2, because that n's replaced with n plus 1, times just that expression itself, but flipped. So -1 n factorial, and then 10 to n. Okay? Well, the absolute value is going to make these negative terms kind of just disappear, because what will be left will be here. Let me cancel them out a bit individually. So I'm going to use red to mess with these. It'll just cancel this out, and you're left with a -1. Here, 10 to the 2n will cancel out. So you're left with 10 to the 2 on the bottom. And then these guys will sort of just cancel out slightly. And you'll be left with an n plus 1. You actually should write that for all of these. Here you're left with a 10 squared. Here you're left with a -1 to the power of 1, just to be specific. N plus 1. Just doing the absolute value and going ahead and doing that denominator, you basically have 1 over 100, that's the epsilon on top, of n plus 1, which is just going to be infinity. And we have the following. It says, if L is greater than 1 or L is infinity, then the sum diverges. So via the ratio test, the sum diverges. Okay, let me just double check that I didn't miss anything. Okay, all right, last one. We have n factorial squared over n 2n factorial. Okay, so I'm going to set this up with the ratio test. Let's see. That's going to be real annoying, but I can just write it like that. We have n plus 1 factorial squared over 2n plus 2 factorial times n factorial squared, and then 2n factorial. Okay. I'm gonna expand this just a little bit before I start canceling things out, because we know that powers distribute over multiplicating products. So sorry, my stutter kicked in. So I'm gonna rewrite that to be n plus 1 times n factorial. However, I'm gonna square this one and this. 2n plus 2 factorial times 2n factorial over n factorial squared. From here, I'm just going to plainly cancel these out. And then from here, there's some canceling, but really, you're just canceling this and you're leaving the first two terms, 2n plus 2 and 2n plus 1. So you have the limit as n goes to infinity of n plus 1 squared over 2n plus 2 times 2n plus 1. From here, Um, both of these numbers will be positive no matter what because n starts off to be greater or at least 1. So therefore, you can just take another step and get rid of the absolute values. And then we're going to use the and then we're going to use just polynomials, like if it's balanced, top heavy, bottom heavy logic to figure this limit out. But I need to distribute both the top and the bottom in order to do that properly. So we have n squared plus 2n plus 1 for the top. And for the bottom, we have 4n squared, uh, 4n, 2n, so plus 6n, and then plus, yeah, I'm just checking, and plus 2. So we see here that it's a balanced equation, and the limit would be 1 over 4. And this limit, 1 over 4, is less than 1. So that tells me via the ratio test that this converges absolutely. So via ratio test, sum converges absolute. Right. I'm just gonna double check that I didn't miss anything here. I definitely did not. Okay, that is gonna be it. So I'm telling you right now, this one is a real doozy because we're learning sort of an amalgamation of things. We had just, 4.1 is probably the easiest because just teaching us sort of the finanglings of it all. But 4.2 is when we're having to start paying attention to recognizing a geometric series, recognizing, convergent and divergence. First, recognizing it of recognizing it of a series and then recognizing it later as a sum. So just keep that in mind, okay? Um, Let me see. And also this like sort of just it keys into like of a series and jumping into of a sum. A sum's going to add up to a real number, it converges. If it does not, then it diverges. However, you can't just do the math, you have to sort of pick it apart. We have the divergence test, we have the integral test, we have the p-series, the limit comparison test. We have alternating harmonic series, but really we have the alternating series test. Then we have um, absolute convergence test. The p-series came up here as well, and arguably so did the harmonic series as well. So maybe we should also remember call the harmonic series. And then the ratio test being the last test we went over. So that's gonna wrap it up. I'm gonna do the group video, I mean the worksheet video next. Let me know if you guys have any questions. I haven't received any questions. Part of me is thinking about maybe just letting you bring a cheat sheet to this exam just because it is sort of notation heavy and logic heavy. But I need to actually like think about it because if I'm gonna do that, so for context, these notes are heavily inspired from a colleague of mine. So I've been using sort of their inspiration to blossom it into this class. And I haven't given a good look at her test as of recording this. So I'm gonna look at their test and see how they gave this test because there is a lot of finesse. Or maybe like, because either if I don't give you a cheat sheet, I can probably give you guys like just heavier instructions. Like, you will use the ratio test to determine blank, blank, or blank. Or to determine one of the three, or determine one of the two. Convergent, divergent, or if it's the three, it's because we're doing absolute convergence, conditionally convergent, and then diverges. So just keep that in mind. But yeah, I'll wrap up this video. I want to practice with you guys, so I'll see you in the next one. Bye-bye.